Hello, everyone, and welcome to our first webinar in the Bedrock Wells webinar series. My name is Leila Gonzalez, and I'll be moderating today's webinar, Bedrock Wells Fundamentals, Regulations, Protection, and Exploration. In today's webinar, we'll be hearing from Ray Talkington and Frank Getchell as they discuss bedrock well fundamentals, well regulations, and wellhead protection, and bedrock well exploration. A little housekeeping before we start. We will be recording today's webinar, and so for audio clarity, we ask that you keep yourself muted when you're not talking. You can find the microphone icon indicated here with the red arrow by hovering in your web browser or in your Teams window. And we'll be having a short question and answer break after each presentation today, as well as a final question and answer session after all the presentations have concluded. And during that time, we invite you to unmute yourself to ask questions. We're going to keep this kind of interactive and conversational during those periods. You can view the meeting chat by clicking on the chat icon indicated here with the red arrow. And here you'll find announcements from us, links to resources, and also you can post any questions or comments that you might have there, and then we'll field those during the question and answer sessions. And then there's a little participant icon there. You can click on that to see the list of participants in today's webinar. And so coming back to our first slide there, please keep yourself muted when you're not talking, and so you can handle that mute and unmute on your own there. Attendees of today's webinar will be notified when CEUs have been issued, and please note that you must attend at least 70% of the webinar for the CEUs to be awarded. In today's webinar, we'll be hearing from Ray Talkington, who is the Principal Hydrogeologist and President of GEOSPHERE Environmental Management, Inc., and he will begin with a presentation on bedrock well fundamentals, differentiating bedrock wells from overburden wells, bedrock aquifer settings in New England, bedrock aquifer water quality variability, and environmental considerations. Ray will also wrap up the webinar today with a presentation focused on bedrock well exploration, covering the selection of a bedrock site, fracture trace analysis, and geophysical techniques. Frank Getchell, who is a senior technical lead at Weston and Sampson, will be giving the second talk today, which will be about bedrock well regulations and wellhead protection. And again, we'll break for questions after each presentation today, and then also have that final question and answer session at the very end. And so with that, I'm going to hand the slides over to Ray.
Thank you, Leila. Well, welcome everyone. Thank you for joining us today. We have a lot of fun on dealing with bedrock wells. We can talk all day on these, but we only have so much time today. So what I'd like to do is just to talk a little bit about bedrock wells and why we're even talking about bedrock wells and why they're important and why we've drifted in the direction of bedrock wells, where we really looked at sand and gravel wells for so many years, but things have changed, times have changed, technology has changed, our understanding of the interaction of bedrock systems and overburden systems has advanced quite a bit. So we're just going to look at this and give you just a sampling of what this is all about today. And next week we'll do a little bit more, quite a bit more, on looking at how we drill these wells, look at some case studies on how we put all the information we're giving to you today and the next week, putting it all together in some case study that we've been working on. Fractures in bedrock, I'm not sure how many people have actually worked in fractured bedrock systems, crystalline bedrock systems, but here we are up here in New England, and we have lots of exposures of bedrock, lots of different rock types too. And what we want to try to do is to understand what these fractures look like in the field when we have rocks exposed that we can look at, what sort of orientations we see these fractures. In the particular slide that you see in front of you now, we have two principal orientations. Do these orientations relate to any regional structural geological trends? Do they relate to cooling fractures within the, say, a granitic type system, or are they some other sort of rationale for having these fractures there? So this is what we're trying to understand as we go along and do all of this. Another little shot of fractures. Here's a slightly different picture of an exposure along a road cut, and we see yellow, one fracture system. We see one parallel to that. Then we have blue one, which is sort of almost orthogonal to that orientation, and then we see a red orientation down below. So not everything is easy as cutting a little pizza up or something like that, where the fractures are always in the same direction and they travel for long distances, but rather they can be finite in size and there can be lots of different orientations. And it's trying to figure out what everything is as the best we can in order to site a bedrock well that's going to give us a maximum yield of groundwater that we can get. So why this type of seminar? A lot of water suppliers, especially up our way, have asked for one. They just like, look, we're tapped out of sand and gravel. We have so many people moving in our area, or the shopping malls find it easier to build on sand and gravel deposits as opposed to blasting rock. So we need to look at something else. There's an increased need for water resources, especially groundwater resources. Sand and gravel ones are hard to find, especially in our area, and we'll show you some pictures as to why we say that. We have some better technology available to find and develop high-yielding bedrock public water supply wells, which in many cases we didn't have before. And a lot of times drillers will go out and, I have this one spot I can drill on, so I drill there and I put a well there. But that may be fine for residential purposes, but for a public water supply well, or even a processed water well or an irrigation well where you want large quantities of water, you need to be a little bit more sophisticated in your approach on how you go about exploring for this. And also we want to put some myths into perspective, because a lot of people would just say, yeah, well, you're not going to get much water out of a bedrock system. It's like trying to get blood out of a stone or something like that, and that's not true. So we have the technology now, and we have people with a lot of experience who are able to find these wells. Now, are we 100% successful? If anyone tells you they are, don't use them, because it's not true. We all have our high percentage rates, but sometimes it just doesn't work out the way we think it should, because bedrock systems are complex. Our objectives today, some background information. Let's look at sand and gravel versus bedrock systems. Is there a difference? Is it a big difference? Something we need to be concerned with? Another thing is groundwater quality. Am I going to get the same groundwater quality in a bedrock system that I am in a sand and gravel system, or are there differences? Regulations. It wasn't that long ago, for example, in Massachusetts, for example, where they didn't even have bedrock well regulations, and they had to be developed, whereas other states have had them for years and years and years. Talk a little bit about exploration. I'll talk about that a little bit later on, and how we go about exploring for this. A lot of these things they do not teach you in school, so it's something you have to learn either by taking classes or working with a company that does a lot of this. Development, wellhead protection, and case study, kind of what we'll talk about in the next webinar on next week. So for sand and gravel or overburden type aquifers, they have variable thickness. They're mostly glacial deposits left over from the last glacial period that around here in New England receded about 10,000 years ago. Most of the deposits that we see, and I'll show pictures in a little while, followed old stream channels, pre-glacial stream channels, and they filled up with some nice stratified drift deposits. Other ones may be remnants of glacial meltwater within the glacier itself that form what we call eskers. Other types of glacial features, it could be a came deposit, moraine type deposits. For example, Cape Cod is marks at the southernmost advance of the last glaciation. So Cape Cod, Martha's Vineyard, Nantucket, Block Island, Long Island were the southernmost advance of the last glacial period, and we see these deposits there. They can be, again, variable thickness from 30, 40 feet up to hundreds of feet in thickness. Pumping rates or yields less than 100 gallons a minute, depending upon where you are and the type of materials, glacial materials, to thousands of gallons per minute in some of these really prolific aquifers, especially these sole source aquifers that we have on Cape Cod and in Western Massachusetts and what's called the Barnes Aquifer System. Hydrogeologically, they can be water table, which means they're unconfined aquifers. They just drill down and you have to use a pump to extract the water from the subsurface, or they can be confined or artesian, where there's some sort of aquitard or impermeable layer above the aquifer systems, like a little piece of bread on top of a sandwich, where the aquifer is the meat inside that sandwich, and when you have to pierce through that confining layer in order to get to it. One that I worked on a number of years ago, a confined aquifer system, had it free flowed onto the surface at 1,000 gallons a minute and had a positive head of 28 feet above ground surface. So there are some really prolific aquifers in sand and gravel deposits. Water quality is highly variable. Locally around here, the pH tends to be around 6. You may get up to 6.5, but with seeing the trends more to the high 5s and low 6s. So a little bit aggressive water, low pH water, slightly acidic, as a function of the rainwater that's falling down, which has a low pH too. Hardness around here is kind of soft. In other places, depending upon the types of sediments that you're drilling into, you may find that the carbonates are big and the hardness becomes a little harder, the water, than it is around here. And you can see that by the incrustations on faucets in your house, shower heads, and you have to periodically clean those so that they don't, essentially the flow rate doesn't drop down. Around here, meaning New England, we see elevated iron and manganese is not uncommon in these particular sediments. It's something that we have to deal with, but they're easily treated, easily removed in most instances. Types of wells. In the old days, meaning 100 years ago, they would put in well fields with up to 100 plus 2.5-inch diameter wells, and they would put them on a suction system, like a big vacuum cleaner, and sucking the water out. Obviously, there are limitations on where the pumping level can be in these wells, no greater than about 25 feet below ground surface, because you just cannot suck from below that. To these days where we have submersible pumps in the wells, or vertical turbine pumps. We've replaced a lot of those well fields, those old well fields, with small diameter wells with submersible pumps or vertical turbine pumps. But most times we just see single wells these days. We periodically have to redevelop these wells, and I would encourage you to, we have another course on this on well redevelopment and maintenance, so you can view that on the AGI or AIPG website. But you periodically redevelop them. Well, why do we want to do that? Because the well screen will get encrusted with iron deposits, manganese, biofilms, carbonate deposits, so you have to clean them out. And we look at the specific capacity of the well to gauge us when we need to do this. The cost of exploration and development is highly variable and depends upon where you are, whether you have to purchase land, what your infrastructure is like, how close your distribution system is, power requirements, etc. So really, really, really variable depending upon where you are. In comparison, we look at bedrock aquifer systems, and bedrock typically is beneath the overburden. The depths of our wells can be anywhere from typically 300 feet to 700 feet below ground surface. Anything below 700 feet, when you're at when you're not on top of a hill, really is the sort of the max depth that we like to go to. Below that, you're not picking up a lot of water. However, that said, if you're up on top of a hill at higher elevation, you're going to simply have to go deeper. It's not uncommon that we've drilled wells down to almost 1,500 feet, 13, 14, 1,500 feet in order to get the water that we're looking for. It's just because we're up at such a higher elevation. Obviously, when you do that, the costs increase significantly because of drilling costs. Pumping rates, this is where the myths are. 10 gallons a minute or less. These are great for residential wells, but not for the application that we want to do for public water supply wells, where we're looking for hundreds of gallons a minute. That's always what we would like to do. I'm just finishing one well, and Frank has lots of stories too, where I have a bedrock system like 850 gallons a minute, so about 1.5 million gallons a day from a fractured crystalline bedrock system, which is a tremendous amount of water. And we'll talk about that one in a case study next week. Type of aquifers, just like we had for sand and gravel, water table conditions, or confined or artesian type systems. They could be flowing artesian or just an artesian well, either one. So hydrogeologically, they behave the same as we would for a sand and gravel well. Water quality is extremely highly variable. It depends upon the rock type, obviously, and the residence time that water has been in the aquifer. So if you're in, say, a granitic type situation where you're looking at a lot of radionuclides in there, you may find that you have lots of uranium, thorium, other type of radionuclides, radon deposits, radon gases within that rock type. Whereas if you go with another rock type that is not granite, you may find, well, you don't have to worry about those problems. You may have other things. You may find that there are a lot of fractures in the rock, secondary mineralization along those fractures, and there could be sulfides, sulfarsenides, and now you have to deal with arsenic or removing sulfur, or just the rotten egg smell coming from the wells. So you may have to deal with that. pH is commonly higher than sand and gravel, not always, but pH is a good guide when we're doing exploration to see what the sand and gravel aquifer pH is, because it may give us some guidance as to where we can explore for our bedrock sources. Again, as in sand and gravel systems, single well is fairly common for bedrock. That's not to say that people don't put multiple bedrock wells in, sited 100, 200, 300, several hundred feet apart, because the way the fractures migrate, you don't want to steal from one well to another well. So you have to be careful and understand what you're doing in order to do this. Redevelopment is typically infrequent, although it's variable depending upon where the water is being captured from that's going into the particular bedrock system. So you have to really monitor that. Again, as for sand and gravel, specific capacity, measuring that is really, really critical. Cost of exploration and development is highly variable, but unlike sand and gravel wells, once you've put that bedrock well in, you have no further costs in terms of drilling. That final well that you put for your exploration will be your final production well. In many cases, at least the way we do it. Groundwater flow in bedrock, I'm sure most of you have seen a diagram similar to this and know all about this, but in the upper right we see pores in unconsolidated sedimentary type deposits where the water flows through those, porosities 25-30%. So we have lots of water flowing through those. It's like, how do we get the water out? When we look at the diagram in the upper right, which is fractures in intrusive rock, I can use a little laser pointer. We see that the fractures going through it, and unlike what we see for pores in unconsolidated sedimentary rocks, in sediments, I'm sorry, it shows like these fractures are here. We may have a porosity of maybe 1% or 2% in these types of rocks, so it's very, very different from the unconsolidated material. But here, ideally, it's shown that these fractures are extending a long way. It's not necessarily the case, but you can see multiple orientations to these fractures. Some are horizontal, some are subvertical in this particular example. Another type of deposit is in the lower left here, which is sort of limestone or marble or dolomite type deposits, where you get solution cavities within this material, and the solution cavities form principally because of the water going through it is low pH water and stripping away the carbonates in here and forming these solution cavities, which are much like fractures, and so they go all different orientations. Sometimes they're huge, other times they're small, but we're looking at something that's not quite the same as we have as unconsolidated deposits. And finally, the one on the lower right are lava tubes, cooling fractures, and in volcanic type rocks, Where I'm pointing right now, you can see the little lava tube in here, and once the lava has drained out of there, you have a nice conduit for the flow of water through there. We see these vertical fractures, which are usually part of the columnar joining within the lava flow itself. We'll see some pictures of that in a minute that I have for you, some examples. And in the upper part here, the cooling fractures within the top of the lava flow, or if it's done in the subsea environment, you may have pillow lavas, which show similar sort of pathways within the volcanics. And also the large vesicles and the large number of vesicles which exist within the volcanic rocks also mimic what you may see in unconsolidated deposits too. Just showing this little picture. Here is an example here where we have, fractures in the red here, which are sort of this orientation, close to being vertical, down below it over here too, the red one, we can just follow it down. We have the green one that's over here, which is almost like horizontal. But we have another peculiar one here, which is the yellow line. And unlike it being a fracture within either cooling fracture in this particular case, or regionally imposed from some regional tectonic event, we can see that we have this diabase dike, basaltic type dike, below this yellow line in this orientation here, and above the yellow line in this orientation. So this is telling us or indicating to us that this lower part of the rock down here where this person's standing, which just happens to be Ted Marine, it's moved off to the lower right here, so sort of normal fault here, whereas this one is above it. So we can connect the actual units here quite easily. So this is a conduit. This fault zone here is a conduit for water to flow through, in addition to these fractures in the rock here in these types of orientations. This one is a little hard to see, but it just sort of shows you the complexity that you can figure to encounter when you do exploration in bedrock systems. In this particular one, there's lineaments that I drew in here from 2012 to 2012, different types of, in 2003, different lineaments that I drew in here based on different aerial photographs. There are also ones in here where USGS lineaments, they tend to be less sparse on their maps, simply because they do it from a higher altitude than what we do. We're looking close at a particular site. In addition to that, there are some very low frequency or geophysical lineaments on here. So we have lots of different lines on here. And it's your job as a person doing the exploration is to understand how these all mesh together. How do I interpret all these different ones? What does it mean? So we'll get more about this, but the complexities here can be really large. What we try to look for, do we see similar orientations on the different air photos? And if it was exactly the same flight line where the photo was taken, the answer should be yes. But in many cases, it's not the same flight line. So the site in question may be in the middle of one air photo. It may be on the left side, right side, top or bottom of another one. So the way the light reflects or the way we interpret it, it may be a little bit different, a little bit off, but we want to put everything together and see how best we can do this and interpret everything that we see. Anatomy of a bedrock well. Here we are, we've actually drilled it. Here's our well going down. What's important here is we look at the overburden material that we've gone through. We can look at the unsaturated versus the saturated overburden material sitting on the bedrock surface, which is highly idealized in this case. We have a bedrock system which is gone through, drilled through the overburden material, gets into the bedrock, and as we showed here, it's intersected like one fracture here, a few fractures down below. And in many cases, we'd like to see these fractures connected to the overburden. We don't always see that, but we know that they do at some point. We also want to make sure that we put in, we like to do 15 to 20 feet of casing into competent bedrock, and then seal that in with a cement bentonite seal in order to form a nice sanitary seal, so we don't have surface waters migrating down into the bedrock system that may bring down contaminants or Giardia, cryptosporidium, or other little bugs and bunnies down from above into the underlying bedrock system. So because we're in New England and we do a lot of this up here, we want to just look at a little picture here of what the sand and gravel or stratified drift aquifers in many cases look like in New England. And as you can see, they're finite in size. They tend to be sort of almost like a north, northwest, southeast orientation in many cases, not always. They're finite in size. They've been filled in with materials that have been washed into the underside of the glacier as it's retreating back to the north, the northern direction up in here. We see down below here in the lower part of the picture where we see Cape Cod, we have Nantucket, Martha's Vineyard. You know, I cut out some of the other ones like Long Island, but this represents the southernmost extent of the migration of the advancement of the glaciers during the last glacial period, which was about 10,000 years ago. We have lots of different types of glacial type features all throughout New England, especially down in Cape Cod. We can see lots of things. These are most prominently seen on USGS topo maps, where we can pick out these glacial features, whether they're esker deposits, whether they're deltas or came deposits. We can actually see these on the actual air photos. Sorry, on the topo maps. But just look at that and you see how sparse the sand and gravel is, but we do get a lot of water from it. Compare that to crystalline bedrock aquifers where they're all completely underneath those sand and gravel deposits. So why we haven't done more work in fractured bedrock systems historically is, you know, a question to be asked and answered, because we have it completely floored throughout here. It's a matter of people not understanding what the fractures look like, where to go to look, and our need for huge quantities of water, which we tend to find more in the sand and gravel deposits than the bedrock system. There are also non-crystalline bedrock aquifers in New England and in the Northeast. If we go out here into the Connecticut River Valley, we have these sort of deposits, which are sort of Mesozoic sandstone and basalts of what we call the Newark group, which extend almost up into Vermont, but extend down into, you know, west central Massachusetts, down into Hartford, Connecticut area, and then it actually goes down into New York, down into New Jersey, and all the way down, paralleling the coastline, all the way down. We even find some of them as far south and west is into Oklahoma. These deposits here represent like a little deposits from an aborted pulling apart of the sort of a proto-Atlantic Ocean way back, you know, 185, 200 million years ago. It started to pull apart here. So we get lots of volcanic rocks and lots of sediments. And then it said, oops, we don't want to do here. And it went off to the east, and it broke it off to the east a little bit more. But we have remnants of what the pulling apart of the continent was, represented in these rocks all the way down the Appalachians in around into the Ouachitas down in Oklahoma. So we see these. In addition, we have some sandstone deposits up here in the northern New York State, and also here through this part of New York, you know, through the Syracuse area, through their Utica, Syracuse area up in here. So these are also represent fairly good types of deposits that we can use. Just a little table here is looking at sedimentary rocks, metamorphic rocks, igneous rocks, and those which are in sort of capital letters tend to be the better ones, looking for water deposits. So gravels and sand deposits are good. Conglomerates, which are essentially cemented together sand deposits, are good. Sandstones, again, the same way, good ones. Limestone and dolomite, because if you remember the picture we saw a minute ago, the solution cavities which exist in those are good. The ones that aren't the best are metamorphic ones, which we have a lot of metamorphic rocks here in the Northeast, but we can still find high yielding bedrock wells in these types of rocks. If we go over to the igneous rocks, you know, basalts with their lots of vesicles in it, lots of cooling fractures, lava tubes in them are pretty good. We don't have a lot of examples of this around here. Other parts of the country, we can go out in the Northwest of the United States, we can go to Hawaii, and these are the types of rocks that make up those good aquifers there. Just a little summary of where we can find these productive bedrock aquifers for basalts and volcanics. So the Connecticut Valley of Massachusetts and Connecticut that we just saw. Sandstone, again, the Connecticut Valley of Massachusetts. And also down to southern New England, there's these Cretaceous deposits, which can be, and we'll see a picture of them a little bit later on, sort of massive conglomerates and some argillites, which are not the best, but still these types of deposits that we have there. And they're pretty good yielding systems. Limestone, dolomite, northwestern Massachusetts. We have some Connecticut, parts of Vermont, and up in Maine. We have some limestone and dolomite deposits. So we don't have a lot of that around here. So we don't use it extensively for aquifer systems. So groundwater quality in bedrock, as we talked a little while ago, granites, which we have quite a bit of, and New Hampshire is a granite state, so we have lots of different types of granites here. Radionuclides are really common, and they're actually easy to remove, but we have radionuclides. Radon, uranium, arsenic are all constituents that we have to be wary of when we look at different rock types and water quality. Secondary mineralization, I talked about this a minute ago, iron sulfides, arsenic-bearing sulfides are actually fairly common along certain portions of the geological terrain throughout, especially Massachusetts and going up into New Hampshire. Certain areas contain huge amounts of arsenic-bearing sulfide minerals, but again, it's easy to remove these. Residence time is important. It's nothing more than the length of time the groundwater is moving through the fractures, and they're therefore in contact with the host rock. The longer it is, the more the groundwater quality will resemble the rock system itself. This is a real challenge for us doing exploration work, whether it's sand and gravel or bedrock, but especially bedrock. It's the competing relationships and demands between the sand and gravel aquifers, of which so many people have tapped into, the underlying bedrock system. We pump the sand and gravel from the sand and gravel, but that's where the recharge is coming from that goes into the bedrock system. So as soon as you begin to diminish the recharge in the sand and gravel system, you then decrease the availability of recharge water and groundwater in the bedrock system. So it's a balancing act on how we deal with this and understanding that. And that's part of doing the exploration, whether it's sand and gravel or bedrock systems. Bedrock aquifer, some environmental considerations, in probably more so in bedrock systems than we have in sand and gravel system. The proximity of surface water bodies in wetlands. Fracture systems can lead directly into surface water bodies in wetlands, and as soon as we turn that pump on, we start to suck that water in from those locations. When we do that, we have the potential to pull in any bacteria, any little bugs and bunnies that may reside in those surface water bodies that get directly into the bedrock system, not having been completely filtered out by those sands and gravels, much like a leaching field. They haven't been taken away. So we have to look at this, and we want to make sure that this well is not groundwater under the influence of surface water. So it's key that we look at this and understand this. Proximity to other private wells or public wells, we typically find that bedrock wells, they extend out their capture zones where particles of water come from that go into that bedrock system can extend thousands of feet away from the actual pumping well. So we have to monitor a lot of private wells and public wells within a fairly large radius around a high yielding bedrock source. Distance to potential contamination sources, again, is really important because we can pull this in from a long time. We have very, very fast times of travel going into a bedrock system. Orientation and length of fractures. That's why we do the fracture trace. That's why we monitor as many wells as we can to understand the orientation and length of fractures in order to understand where water is coming from that's entering into the bedrock system and therefore into the well I'm pumping from. Recharge areas, cannot say enough about this. Your old thought process on sand and gravel wells and where the water's coming from, you kind of have to throw it out because bedrock systems do not obey watershed divides. They go right past them. They blow right past them. So you have to understand this, and hence why orientation and length of fractures is important. And all the stuff I'm presenting to you is critical that you understand and know this. Wellhead protection areas, they're not typically what you see in a sand and gravel system. This particular one, which was done quite a while ago, there's sort of a curvature area in the lower left down here, and that's simply, we couldn't find anything down there, so we just put a radius around the bedrock source, which is here, right next to this reservoir. But we could see drawdown up this wetland system up in this direction here because we recorded fracture zones, which were coming from here up into this direction here. So we could actually record some drawdown, which was occurring up here, going underneath the reservoir and up into this area here. So we had to draw our capture zone, or in this case, we call it a zone to delineation, in this particular case, Massachusetts, to look something sort of odd shaped and not something you typically would see. This one here, for anyone who's ever drilled a bedrock well, the joy of seeing water coming from that well as you're drilling it is always sort of a rush when you see this. This particular well, I'm going to put on a minute. There's no real sound to it, so I'll talk over it as we're doing it. This is a well that's being drilled. This is particular one is in New Hampshire. We can see all the different tools that are here, but Ted Marine will talk about those next week. But this well is being drilled, and water is blasting out of this well at about 400 gallons a minute as he's advancing it and as he's drilling it. He was not able to lift the water out of the borehole with just the drill rig, but he had to put an auxiliary compressor next to it so he could put more air pressure down, which is this other green vehicle right over in here. He had to put that down there simply because he couldn't push the water out. So he's pushing this out at roughly 400 gallons a minute. This particular well has been told to us by the regulators in New Hampshire is the largest producing public water supply well ever in the state of New Hampshire. And it'll do like 850 gallons a minute, which is a phenomenal amount of water for anyone who's ever done a bedrock well knows that that's a tremendous amount of water. There's a lot of information that you have to come up with in order to see how far are these fractures extending, where's the water coming from, am I going to pull in any salt water? And this will be part of the case study we talk about next week, and I will lend that there. And if there are any questions, just let me know.
Great, thanks, Ray. I'm going to go ahead and take back control real quick.
Okay.
Here we go. So if anyone has any questions, please go ahead and unmute yourself and ask away. I do have one question about, you were talking about groundwater well demand increasing, especially where you are up in New England. Do you see that as a trend across the U.S., or is that regionally specific to where you're located at?
I think we're seeing that throughout the country, especially areas where people are moving into. The Southwest is a huge example. In Arizona is a big place where people are moving into. Obviously, California is huge. You look at Texas, you look at Florida, all places that people are moving into right now. Just a huge demand for water, not only for personal consumption, but also for irrigation purposes, for just agricultural purposes too. So we have a tremendous amount of demand as population increases, as the demand for food increases. We see more and more demand for water, and it's our job to try to find it the best we can.
Great, thanks for that. One other question I had here was, you're talking about bedrock wells being able to produce more than a few, basically 10 to 100 gallons per minute. What are some characteristics of the ones that are exceedingly high flow rates, maybe over a couple hundred gallons per minute? Can you talk about that a little bit?
Those are interesting ones. We do our best to try to identify fracture systems. We'll talk about this more in a little bit later on, but we try to find where there are a greatest number of intersecting photolinears as part of our fracture trace, and then we'll just drill through it and try to find out, are we going to intersect that? So there's no real magic wand that we have or crystal ball to find out, to identify whether we're going to have tremendous amount of water or not. We just don't know. Traditionally, a lot of these bedrock wells. If you can find 150 gallon to 200 gallon a minute bedrock well, that's really a good well, and it should sustain for a long period of time. More than that, and you've done a really good job, or you're extremely lucky.
Great, thanks. We have one question from Emmy who's asking, is for bedrock wells, is cement grout preferred to, I believe, a bentonite grout?
I think you can use either one. We've used both. Doesn't matter. You're just trying to seal off the overburden from the bedrock system, especially close to the bedrock overburden contact or interface. Typically, or at least around here, we find that the upper part of the bedrock system tends to be weathered and fractured. So we want to seal that off as best we can from the more competent rock that's deeper down. Unless the state has certain regulations in which they require to use certain type of cement bentonite mixture as your sanitary seal, and that's really guided by the regulators of your state. Oh.
Gotcha. Does anyone else have any questions? Feel free to go ahead and unmute your microphone and ask away if you do. Okay, I guess not. So we'll move on to Frank's presentation next. Thanks, Ray. And we'll go ahead and move on over to Frank.
Great. Good afternoon. Thank you. Thank you, Layla, and thank you for that great introduction, Ray. I'm going to focus on some of the regulatory aspects of bedrock wells and related aquifer wellhead protection, specific to several different states. What are some of the concerns that regulators and the users of these supplies have expressed, and how are they dealing with them on a regulatory basis? It's kind of back to Ray's point. Here's your typical superficial geology map of the lower 48 states. And you can see from the various colors, there are numerous formations that occur within the boundaries of our country. The one thing that is consistent, though, is that bedrock underlies its entirety. Unconsolidated materials are going to be locally occurring, sometimes regionalized, sometimes much more localized, kind of like Ray was pointing out earlier about some of these sand and gravel deposits that occur in New England. I think one of the things that has occurred over time is that the unconsolidated deposit aquifers were commonly the first to be developed because you didn't have to go too deep to get them. In a lot of instances, they were connected to some surface water bodies, so there was a lot of recharge available. And they were more predictable in terms of how to deal with them. And in some instances, they were actually more preferred by regulators relative to public community supplies. Bedrock aquifers, on the other hand, were often developed in areas where they were the only source. But with that would come the cost associated with having to go deep in many areas. And in some areas, they were only locally of high capacity. So that would obviously have a bearing as to, why the preference in certain areas for unconsolidated deposits, aquifers versus bedrock. To keep things kind of in focus, because obviously we have 50 some odd states here, and on a statewide level or on a regional level, sometimes within watersheds, sometimes within management districts, we have specific regulations. I'm just going to kind of focus on the Northeast to kind of coincide with where Ray has been already, but also because the Northeast has a pretty good cross-section of the different types of geology, I think, that is elsewhere in the country. And as far as the bedrock types, we have, igneous, metamorphic, sedimentary, and then the different subsets associated with those. And historically, it's probably one of the areas where groundwater as a water supply has been historically developed for a long time. So with that said, I'm going to first look at, just to kind of focus in a little bit. We have New England and we have what are called physiographic regions. For those of you who are not from the area, you can see it's pretty diverse. Each of these regions corresponds to different types of geology, bedrock, surficial. And these physiographic regions do extend southwards into the rest of the mid-Atlantic and Northeast. These are some of the oldest rocks and some of the youngest rocks actually within the country. Besides rock types, we also have varying different degrees of structural provinces. We have layered rocks, we have fractured rocks, we have folded rocks, faulted rocks, and so forth. And each of these different types of rock types and provinces lends to different types of bedrock aquifer formation and approaches as to how to develop them and what the yield capacities may be. So, how did we get here? Well, this is an off-take of what Ray was showing. You can see the areas that, where there's extensive sand and gravel deposits. As I said, I'm going to call it the easy groundwater. These are the areas that early on were historically developed. But as you can see, percentage-wise, over the entirety of, say, New England, and I'm going to throw New York in there, you're looking at probably less than about 30% of the overall area. So that leaves a lot of areas where sand and gravel is not a viable groundwater supply, and bedrock is. And so what has happened over time, there's been more and more turning to bedrock as a source. And in some instances, they're in areas where there is no sand and gravel. And in some areas, you may actually find that the bedrock underneath the sand and gravel is being targeted. And, that's starting to cause a little bit of consternation with the regulators, because it's one thing to deal with sand and gravel. It's more predictable. But when we start looking at bedrock, as we'll show later on, it's not so predictable. And in some instances, we may be competing for the same resource. Bedrock, again, is to take from a slide that Ray had. You can see that we have a lot of different types. Most of New England is underlain by crystalline, metamorphic, and igneous rocks. We have some localized areas in Connecticut and Massachusetts, and we'll see later on into New Jersey and Pennsylvania with these Triassic sedimentary rocks. And then once we get to the other side of the Hudson and looking at New York State, the bulk of that is underlain by sedimentary rock, ranging from carbonates such as limestones and dolostones to various types of shales and sandstones. And each of these rock types kind of possessing their own characteristics when it comes to groundwater yield. If we move further to the south, a lot of these units do continue on. So some of these other states, such as Pennsylvania, New Jersey, Virginia, and so forth, have been also dealing with the same types of issues relative to the development of bedrock groundwater supplies. And as with the New England, we do have some continuity of some of these sand and gravel deposits that are associated with glacial activity in the area. But again, you can see that these sand and gravel deposits, with the exception of, say, the coastal plain, which we'll talk about quickly, they're kind of spotty. They tend to correspond to some of the major river valleys. The exception being, let's see if I can get to one of the tools here. I guess I can't. Bear with me. Here we go. Pretty much the area of southern New Jersey into Delaware and the east coast of Virginia and Maryland and so forth are underlined by a sequence of Cretaceous unconsolidated deposits that can range upwards of 17 to 1,800 feet thick. These are great resources of groundwater, but it's sand and gravel. They're expensive sources to develop because of the depths that one has to go in. And as with the other sand and gravel deposits, they can be overdeveloped. When it comes to bedrock aquifers, I would hazard to say that a lot of New Jersey, southern New York, eastern Pennsylvania have probably seen more development as far as bedrock goes primarily because of the Industrial Revolution, and in terms of a lot of the area where they didn't have hydroelectric sources or surface water sources for water, groundwater was pretty much at the top of the list in terms of providing those supplies. And so historically, those areas have been much more developed as far as bedrock goes. And you can see why. You have that same Triassic, those Piedmont sandstones and conglomerate units that Ray referenced that are up in the Connecticut River Valley of Connecticut and Massachusetts, extending for a much greater area. You have some of the crystalline rock that also occurs up into Maine and Vermont and New Hampshire and Massachusetts. And then when one goes to the west, you have some significant amounts of sedimentary bedrock that's relatively layered, flat. There are some limestone units in there that are extremely productive bedrock aquifers. But you're also getting to parts of the country where the development and needs for industrial use are not quite as significant. So it's still kind of spotty. So with all of this comes the question about regulating bedrock supply wells. All of our states, at least since the turn of the century, and probably more so within, say, from the 1950s on, have been regulating groundwater supplies, recognizing that these supplies are in more and more demand for both drinking water and industrial uses. And so some of the techniques that have been applied for the regulating of these groundwater supplies, at first blush, start to get transitioned or transferred over for bedrock. But what's been recognized quickly is that bedrock aquifers don't behave the same as sand and gravel aquifers in most instances. So what I'd like to do is talk about three main areas that these regulatory concerns are specific to bedrock wells: well construction, yield with respect to recharge and not exceeding the capacity of these aquifers, and then finally wellhead protection, which is a relatively newcomer, but I think early on has been recognized as a factor that needs to be addressed, especially when we start realizing that the water that we develop from a bedrock well or bedrock aquifer doesn't necessarily come from where we think it may. These concerns are going to vary by state, and in some instances they also vary by the bedrock type. In some instances, limestone, dolostone are treated different than sandstone, are treated different than shale, or treated different than granites or basalts type aquifers. I'm going to provide you with examples from several northeastern states just to kind of keep the discussion kind of targeted and within the time constraints. And one thing I do want to point out is that we're usually talking about supplies that are 50,000 gallons per day or greater as a threshold. So really, I'm not going to be focusing in on, say, domestic or small individual wells. We're going to be talking more in terms of wells that are used for public utility purposes, public community supplies, industry, and so forth. So with that said, let's just look at well construction as the first. As Ray pointed out earlier, most of the bedrock wells within this region that we're focusing on are usually going to be drilled with downhole hammer or air rotary techniques. These are your typical type of rigs. You're looking at usually 20-foot rods that are advanced. There's usually a hammer in front of these that are pulverizing the rock as it's encountered. The driller will use techniques like back pressure to get a sense as to whether or not they've encountered some decent water and whether or not to continue on. Cuttings are returned to the surface, usually at the foot of the casing, and the driller and geologist, hydrogeologists, are able to get a sense as to what bedrock unit they're in, what the nature of that unit is in terms of how it's broken up. The regulatory constraints associated with these types of wells and what are a concern are things such as casings, minimum casing length, how much into the bedrock should the casing go, the number of casings. Should there be a surface casing? Should there not be a surface casing? The extent and thickness of the annual seal. In other words, I think there was a question earlier about, grout types, more so in terms of how much grout and what's the minimum thickness. Whether the casing should be driven into the bedrock or should it be drilled in and set into a socket. So these are types of things that the states look at relative to the construction of these wells. Let's keep in mind that, just from a general perspective, we look at casing as a method to maintain the integrity of the borehole, especially when we're in overburden materials that tend to be soft and collapsing. We want to maintain the integrity of that material and prevent it from being able to go into the well. Once we get into the well, the casing will go into some minimum depth. Its intent, as Ray had pointed out earlier, is to minimize some of the surface water from getting down into the intake portion of the well, potentially contaminating it. And then we have the intake itself. And usually in most of the bedrock that we deal with, it's an open hole. The bedrock is competent enough to maintain itself in terms of from collapsing. Though there may be some instances where some of that rock may be excessively friable, and in some instances, screens may be used as part of the construction technique for these types of wells. To give you some comparisons, at least into the Northeast, in Massachusetts, the casing must be grouted 15 feet into the bedrock, and with adequate annular space at the bottom to extend 35 feet below the pump setting. So what happens here is we're not only controlling the seal around the casing, but we're also kind of setting a minimum depth requirement on that open hole. We want to maintain a separation from the bottom of the pump and the bottom of the well. That's pretty much prior, that's kind of protecting the pump itself, looking at some of the soft zone, and also looking at the fact that the bottom of most wells, whether they be screened wells or bedrock wells, tend to be where some of the poor quality water tends to kind of accumulate. In New Jersey, the casing must be set a minimum of 20 feet into competent bedrock. So we're actually specifying the quality of the rock, and it must go into a socket. So what that means is that the casing isn't just driven into the rock. We actually have to drill a 20-foot borehole into the top of the rock, set the casing into that, and then seal it in place before we continue on with the intake portion of the well. There's an overall casing length minimum of 50 feet. So that's specific to that state. If we go to New Hampshire, the casing must be set a minimum of 10 feet into competent rock, and a drive shoe is permitted. So what that means is that we don't necessarily have to open up a borehole and set that casing in there. We can actually pound it into the rock and then drill it out. And then grouting would take place between that set casing and the overburden up to some depth. It doesn't specify what that depth should be. Pretty much because of the depths of bedrock in most of the New England states, probably looking at about 30 to 50 feet. In New York, casing length and need for grouting is dependent on the bedrock and overburden type. So not only do we look at the nature of the bedrock as to what the casing length, but we also look at what the overburden is. We usually result in a minimum length of 19 feet, relatively odd number, firmly seated in rock. And then as far as the grouting goes, it really depends on what the nature of the overburden is. The overburden can be weathered rock, it can be till. If it's sand and gravel, the state recognizes the fact that trying to maintain grout in a coarse permeable zone is a difficult one. So they actually allow for the grout not to extend into the sand and gravel. So it just gives you an idea of the variability of what takes place when we start looking at standards. In some instances like Pennsylvania, basically what we just look at is go by the AWWA standards. And if you haven't seen that, that comes under A100. And they just require a minimum thickness of grout of 1.5 inches. So what about yield? Again, public community supply wells, usually what happens, there are other aspects of these wells besides in terms of how much water they produce. It has to be linked to some sort of confidence. and for permitting purposes. So usually what will happen is there'll be minimum requirements for testing in terms of how much water in the long term can be developed from these supplies. And why is that? In sand and gravel, we usually have a pretty good sense as to how much water we can get from sand and gravel, where the recharge sources are. When we start looking at bedrock aquifers, it's a lot different. This is a typical terrain in a highly fractured and faulted crystalline type rock, metamorphic type rock. You can see the angles that are typically associated with these fractures. As one gets closer to the surface, the fractures tend to kind of mimic the bedrock topography. They don't necessarily reflect the structural aspects of the rock itself. And so the question is, when I put a well in, where is the water actually coming from? And what are the sources of recharge? Are they coming from other rock units? Are they coming from sand and gravel? Are they coming from surface water sources that are hydraulically connected with the sand and gravel, and then in turn is connected with respect to the rock? So as a result of that, a lot of times what we'll do is we'll look at the requirements for testing to try to address these issues. You know, in the case of fractured sedimentary rock, it's a little more predictable. If it's karst, it's a little less predictable because there's a lot of storage. You can see we're not just riding along the surfaces of the fractures. We're also looking at some of these voids that can have some significant volumes, and a lot of that water takes a long time to drain to get to where we're looking for. One of the things that you'll hear about a lot with respect to rock aquifers and how water moves is anisotropy. And anisotropy is going to reflect the orientation of the fractures and the aperture size of the fractures, and whether or not they're vertical, semi-vertical, planar, or what have you. Here's just two plots of a typical pumping test data for a fractured rock. This happens to be a crystalline rock. On the left, you can see a plot that shows what happens over time, time drawdown. You can get a sense as to how significant a lot of times these drawdown values are. You see a series of, inclines, bounce backs, inclines, bounce backs, incline, bounce back. And these are all reflecting where the fractures are, reflecting the fractures that actually are providing the source of water. And so when the state looks at pumping tests, it wants to know this. It wants to know, what am I relying on? Am I relying on just the yield here? Am I looking at the yield here? And am I running the test long enough so I know whether or not this is a fracture or an aquifer that isn't necessarily looking at one significant groundwater recharge source, or is looking at more of a series of groundwater recharge sources. And likewise, when I look at the influence on other wells, you can see this anisotropy that I'm mentioning really is what accounts for the variability that you see as far as drawdown based on observation wells as one gets further away from the supply well. So when you look at pumping test requirements in Massachusetts, as an example, step rate tests are required. And they need to be, basically steps that correspond to 200% of the proposed rate. And then they're followed by a 10-day constant rate test. So what we're looking at is making sure that we have enough time to allow for all the sources of influence to contribute to the yield of a well. Along with these tests usually come the requirements for observation wells and a significant distribution of them. In New Jersey, step rate test is recommended and only a 72-hour minimum test is required, but it's at 120% of the target rate. Stabilization is looked at. New Hampshire, constant rate test is just a minimum of 48 hours, much shorter time frame. In New York State, it's 72 hours, but stabilization needs to be reached. If it's not reached, then testing may be required to continue on. If it isn't, one needs to extend the drawdown rate for 180 days to get a sense as to how reliable that supply is. And then lastly, wellhead protection. A lot of times this will be actually regulated not necessarily by the permitting folks at, say, who basically permit looking at diversion amounts, but by the Department of Health, the state aspect of that. And why is this important with fractured rocks? Well, a lot of times we look at wellhead protection. We look at it relative to uniform flow. When we talk about bedrock aquifers, it's a little bit different. Typically, we look at wellhead protection in terms of zones or tiers. They're usually linked to some sort of time of travel based on the nature of particular contaminants. A lot of times, contaminants close to the well are the ones of most concern because they take the shortest amount of time to get to the well. This tends to be an area that we kind of concentrate relative to bacteria or viruses because they are the shortest lived. And no matter how we look at a lot of the synthetic contaminants that are out there today, they're usually of most concern. So when we look at bedrock, it's a little bit different. It's not so uniform. One of the things to keep in mind is that groundwater and contaminants move at a macro and micro scale. Ray mentioned this earlier about time of travel. And a lot of bedrock aquifers, the shallow groundwater in bedrock may be on the course of less than 10 years. There's an intermediate zone that's 25 and a large zone that's can be over 40 to 1,000 years. And the longer that groundwater resides in the subsurface, the more mineralogy, the more chance in terms of how far out we'll actually be transporting contaminants. The block diagram on the right gives you an idea of some of the circuitous routes that some of the groundwater and some of these contaminants may take. And this needs to be taken into account when we start looking at wellhead protection areas. To give you an example, here's a comparison between uniform flow, where we first started, where we have a nice elliptical shape and gives you an idea of the time of travel. Whereas when we talk about bedrock, proximal to the well, we may have something that's very close to this type of contributory area to the well. But as we get further and further out, we have groundwater that's going to be traveling following the paths of a lot of these interconnected fractures. This also accounts for the high yield, but also accounts for us pulling in contaminants from much further distances away. So as a result, when we start looking at wellhead protection areas from the state perspective, in the case of Massachusetts, we have what are called Zone 1, 2, and 3. Zone 1 is, looking at the area within 400 feet. Zone 2 is what's called the capture zone at 180 days. A lot of this is going to be established based on the pumping test and based on the layout of the fractures as we identify them. And that goes into play when we start looking at our wellhead protection areas. And Zone 3 can go further to the extent of the aquifer and even to the boundaries of the watershed that contributes recharge. In New Jersey, we have what are called tiers 1, 2, and 3. We base those on 2-year, 5-year, and 12 years. So in other words, how far out does groundwater travel within 2 years to the well, 5 years, and 12 years. And within each of these tiers, we identify certain types of land use that are not appropriate. Keep in mind that with all of these, there's what's called a minimum control. In New Jersey, it's only 50 feet. Purveyor needs to be able to control the area within 50 feet of the wellhead. When we go to New Hampshire, they need to be able to control 200 to 400 feet. And the wellhead protection areas for bedrock needs to take a look at 1,300 to 1,400 feet based on the yield and the fractured nature of the aquifer. And what we need to do is identify and take an inventory of what the potential contamination zones or land uses are in those areas, and look at local land use regulations either on a municipal or statewide level to help control those. In the case of New York, there's a minimum ownership of land of 200 feet. And then there are certain setbacks from different types of land use. New York, pretty much that's the teeth of that process. The Department of Health only requires on top of that identification of the aquifer extent and fracture extent that contribute to the wells and what the land use is in those areas and potential contamination. And that in turn gets pretty much disseminated out to the local municipalities for consideration relative to their future land use. With that, that's it for me on the regulatory standpoint, from the regulatory standpoint relative to bedrock wells. And again, I'm only focused in on the Northeast. It's safe to assume that as one goes throughout the rest of the country where bedrock wells are a significant source of water, that you're going to have regulators also looking at construction and testing and wellhead protection requirements.
Great, thanks, Frank. So we'll take a short break here for questions again. So if anyone has any questions, I encourage you to go ahead and unmute yourself so that you can ask Frank any questions.
So this is Chris. Frank, I got a question. When you're working, if your company's working across several states, do you end up establishing company-wide sort of the most practices that use the most restrictive regulatory components, or do you feel that each of the states have good grounds for some of the differences that they have in some of their requirements?
That's a good question, Chris. It's just, at that last slide, or the last couple slides there, you can see that the states do vary significantly. Obviously, one needs to follow, what the regulators are asking for specific to pumping tests, construction, and, wellhead protection. But in the absence, or where some of those requirements might be a little lax or ambiguous, the effort usually is, an ounce of prevention is worth a pound of cure, is to follow kind of, best practices, best management practices, I think, that anticipate future changes in those regulations, anticipate future land uses in certain areas, and if it's viable and the client is on board, and this is where education comes in, I think the prudent thing would be to go for the more judicious and the more restrictive approaches to those aspects of bedrock well construction and testing. One thing I will say that which we're seeing a lot of, like Pennsylvania is a prime example. Pennsylvania requires that professional geologists be involved with these processes, all the way from the permitting of the well construction to the testing to the wellhead protection. And so as a result, we get to actually play a much larger role, and I think an important role, based on our experience and understanding of what does take place in the subsurface. And there are several states within the region that I've just identified, that do have licensing. Some of them are not quite as strict in terms of those requirements. And there are others, as you go elsewhere in the country, that are just as strict, if not stricter.
Great, thanks. I have a question here from Emmy. Is dye tracer testing ever used to delineate wellhead protection areas?
That's a good question also. It's not necessarily required, but in some states, especially in terms of karst, as an example, where there may be a question regarding, delineation of the wellhead protection area, because of some ambiguities in the aquifer testing or modeling, it can definitely be used as a supplemental technique to help identify those wellhead protection areas. One of the things, as an example, in New Jersey, the state actually does wellhead protection area delineation using an analytical approach for all new public supplies and existing public supplies. In some instances, the purveyor of the particular well may opt for a more stringent wellhead protection delineation, and that's one of the techniques that may be used. But it's not necessarily, I've ever seen it used on its own or used that frequently, at least in the Northeast, but it definitely is a tool that has been used.
Great, thanks. Do we have any questions from anyone else? All righty, well, I think we'll pass it back over to Ray for our last presentation.
So what I'd like to do is sort of continue on from what we've been talking about and look at actually bedrock exploration and how we do some of this stuff. It's not a simple solution. You just don't go out and just let's just drill here today. And that's what a lot of people, especially developers, like is just put a well over here somewhere. Or architects like that too. They've designed everything and then they want you to get the most water to do whatever they're doing, but you only have this postage stamp upon which you need to drill. So we appreciate what everyone else has done, but it's always better to have us go in first, try to find the most water that we can that's designed for the project, and then sort of back into it. So we have to ask ourselves some questions, like where do I start? Has the area been mapped at all? Do we know anything about the area? What are the rock types like? Because we want to understand, what rocks are we dealing with? Are we going to find a lot of fractures? What's the water quality going to be like? What are the structural elements? Is it highly fractured? Is it lots of tectonic activity that has gone over here in the past? Things that I can look at. And most importantly, how do I see below ground surface? How do I look below there and see all these different things? These are all the questions that we ask ourselves when we're going to do an exploration project. When we do it, has to be a phased approach. You have to understand local water resources, what's happening there, who am I competing with by putting in a bedrock well? Is it some other public source? Is it a fisheries? Is it agricultural? Is it residential? What am I dealing with? And using a systematic but also really pragmatic approach, and we've been hearing about that from Frank and what we've been talking about, you need to look at what's the geology, what's the hydrogeology, do you know a little bit about geophysics? Why do we need to incorporate all these things? Kind of doing bedrock exploration is we have to put a lot of things in this sort of little container, shake it up and pour it out, and we get to the groundwater exploration and how we do it. Compile all this information, and there's a power using GIS data layers to do all of this stuff because we can turn them on and off and see different things. And also what's critical in all that we do hydrogeologically and geologically is to develop some sort of preliminary conceptual hydrogeological model about where we think water may be coming from based on information that we have gleaned from looking at some of our background existing information. This is all pretty. We're looking at pretty pictures, but it's a phased approach. How am I going to deal with these surface water bodies here? How am I going to deal with the layout of this golf course and where I'm going to put wells? Where do they have their water hazards, i.e. their irrigation ponds? Where is this? Now that they have the whole golf course in, how are they going to put the piping in when I find a good source for them? So it's understanding all of this and doing it in a phased approach and getting in early. As Frank mentioned, getting it early to do this as opposed to after all of this has been done. We've looked at this, how groundwater flows through fracture systems. Frank talked a little bit about, the karst type topographies, but we're really concerned with what's going on in B and how water travels through those fracture systems. Again, we saw this picture a little while ago where we have the fractures through here. These fractures here, subvertical ones like this, I actually labeled them in this particular diagram. We have our fault zone coming through here. So we have fault zones, we have fracture zones, and that's why it's important to be able to recognize these and to be able to trace them geologically as far as you can, as best that you can when you're doing your work and building your little pictures. This is a picture of columnar basalts jointing in a volcanic a lava, essentially a flow and a sill, if you like. These are the cooling fractures between the columnar joining in the lava flow. And then we have the top of the lava flow up here, which will have more vertical fractures and some horizontal fractures, or an anastomosing network of fractures up through here. And sometimes we find pillow lavas at the top, but this is what we're looking at to try to understand how water is going to travel through all these, essentially the thickness of this lava flow, in order to, where do I site my well? And notice not all these fractures are vertical. In this case, they come up, they curve on you like this. So these are all things we have to understand and take into consideration when we're doing our work. Because it's easier to see water flowing through fractures when they're frozen, we have a lot of pictures here of fractures when they're actually frozen here. So here's a main water-bearing fracture zone in this particular case. Notice that it tends to be more horizontal than vertical. The one below that also, tends to be mostly horizontal fractures that we see a lot of the water coming through. Again, down here, notice not right at the top, but it's a little bit deeper down. For some particular reason, it could be it's a larger fracture zone, which everything has come down, and these horizontal fractures tend to be tighter and closer together. Not a lot of water will flow through them, and then hits this one here, and it tends to be, you know, the magic wand one where all the water is coming through. This particular one, we see water going through a number of different locations. This is not frozen, but you can see it flowing through a lot of different locations, but principally through this one over in here and this location over in here, and not much water here. So if you drill down and through here, you may not have much water. You step over a little bit, you have more here, or step over, you have a little bit more here. So you have to understand, put all this geology together to get a much, much better picture. Well, if we did have a crystal ball and we look down below ground surface, and we can do that in this particular one, fractures in crystalline bedrock, and here we're looking at a downhole geophysical log, acoustic televiewer or optical televiewer log, and we're going down. Here's the actual rock surface itself, sort of wrapped around sort of in 360 degrees, and you can see the structures in the rock. It kind of looks like sort of U-shaped or V-shaped, but this is the actual fabric in the rock as we're looking down. We come to this point down here, and we can actually see the hole, the fracture zone down and through here. And this is what it looks like. It's not very large in many cases. And you know, we typically have seen them maybe 1 inch, 2 inches or so, and they tend mostly to be not quite vertical, but horizontal or sub-horizontal. You also get the orientation of the fracture zones by doing this downhole geophysics. But this is the main water-bearing fracture in this particular borehole here. So it doesn't look like anything what we're seeing on the surface, but this is where the water is coming in this particular borehole. So when we're doing exploration, we definitely have to take a phased approach. Look at your background data and maps. You have to collect as much data up front as you can, because you don't want to reinvent the wheel. You want to find out if some work has been done. How can I use that? How can I integrate that into my phased approach? The hydrogeological analysis, you know, what are the water resources? What are things looking like out there? What am I competing with? So pull all that information together. You have to get out of your car, you have to get out of your office, and you have to get out into the field to do the field reconnaissance. Can I find any bedrock exposures out here? And if so, let me collect as much data from them, strike and dip orientations, you know, fracture density, whatever it may be. We'll talk more about it later on. I want to be able to do that. Potential contaminant survey, absolute is a key. A lot of times, most state regulatory agencies have data layers, GIS data layers of known contamination sources. And it's good to be able to get those, pop those on your map, your GIS map that you have, to find out, okay, are there any potential contamination sources? And if so, what am I dealing with? And do I think they'll be within my capture zone of my well? And then finally, we want to explore favorable areas and select our drilling targets. This is always the fun part at the end, when you put all your information together to get out and actually begin to see how good of a job have I done? Are the rocks going to be really receptive to having a well put in them and withdrawing groundwater? So in terms of background data and maps, you know, good sources of data and maps, you know, always go to USGS maps and reports. That's their job. They've been doing it for many, many years. There's lots of data out there. Use those to give you guidance on what you're doing in your particular site. State and local agencies, the state will have compilation of work that's been done. It may not be in publication form. You may have to do, data searches there, either online or actually physically go there. Local agencies may or may not have something. They may have information on wells that have been drilled there, and you get information from them. It's spotty at best in many cases. Talk to drillers. Drillers are the ones out drilling these wells, and a lot of them have lots of information on what they've found. Now, they may call every rock that they drill into granite when it's really not granite, but that's maybe what they call it. So you have to understand what they found. Is it highly fractured? Do they get good yields? What are they looking at? And sort of not as a last resort, but as an arrow in your quiver, is to talk to homeowners, especially if you're going to be drilling and you may have to use their wells to monitor as part of your pumping tests later on. talk to them about their wells. Many cases you'll find there's not a lot of information because most people don't know anything about their wells, if they have one, how deep they are, what kind of pump they have, or anything like that. But it's still worth reaching out to them to find out as much information as you can. For the hydrogeological analysis, understand where your drainage basins are, do a drainage basins analysis, understand your groundwater divides, but be careful. As we saw in diagrams Frank had up and what I mentioned earlier, fractured bedrock systems do not behave the way you would like them to do for sand and gravel. They don't care about those divides. They go right across them. So you have to understand that when you're putting your stuff together. Your recharge analysis, what's the interaction between surface water and groundwater? This is critical to know this. As Frank mentioned earlier, you've got to know this because you want to make sure you're not pulling in so much surface water that you may have an issue with water quality or bringing viruses and bacteria into your well. And look at your existing well information because this can help you put together your geological cross-section through an area to give you an idea of what the rock types are, where fracture systems may be. And another one, and we're concerned with that here, at least along close to the ocean, is salt water a concern? Am I going to start pumping a well, and all of a sudden drawing salt water into it, which would be the kiss of death for a well, because once you have that salt water in it, there's no way that you can recover that well to be useful as a potable water supply. So just a little cartoon for hydrogeologic analysis. Look at these interactions. Understanding what's going on here at the surface, where my rivers are, what's connected to. Recharge basins, agricultural fields, which may be a source of contamination. What type of surface geology, subsurface geology is there? Is it all sand and gravel? Are there clay deposits here? Are there aquitards, which I should be concerned with? What's the potential for recharge to the underlying bedrock? So understanding all of this and what's going on is really, really important for developing that preliminary conceptual hydrogeological model. Field reconnaissance. For those who are geologists, hydrogeologists, I mean, to be out in the field is the best thing that you would want to do. Windshield surveys are great if it's the wintertime, but you want to look for rock outcrops. You may have a geological map of the USGS, which is showing you rock outcrops in the area. Go visit all of those. Use topographic maps and GIS data layers to identify streams, wetlands, glacial features, etc. This is important too, because this will give you an idea of what's going on there. What potential do I have for recharge in my area? Are the wetlands sitting on perched clays such that I'm not going to get a lot of recharge from them? Are the streams losing streams? What are we dealing with? What type of glacial features do I see? Examine any and all visible outcrops to identify rock types, structural features, measure strikes and dips. Yes, you have to use your Broughton compass of layers, measure foliation, fractures, fracture density and orientation, and you put this all together in your little picture for developing your model as to where I'm going to drill, what are the likelihood that I'm going to see. If you have, for example, structural features where you're only finding fractures every 100 feet apart in the rock types you're looking at, well, it's kind of telling you that maybe in the subsurface you're not going to find a lot of fractures. You're just not going to, because they just don't exist in this particular rock type. So that's why it's a key to be out there to look at these. Here's an example of actually going out in the field on this particular rock outcrop here and actually measuring the strike and dip of these particular fracture zones that we're dealing with here. Measure them, plot them up on your structural net and see what you're looking at. Do any of these follow major structural regional trends of areas, or some of them orthogonal to that, which typically you find? What am I looking at? These will all give you guidance. And look at the actual fractures themselves. Are they slick and sided? Do they have mineralization along them? Are they nice and clean and smooth? And that will give you an idea of what they may look like in the subsurface too. PCS is potential contaminant survey. Windshield survey to look for them, although you'll have it on your data layer. that you get from the state or local agency, mostly the state. Review all these agencies. It's really, really important to do this. Contamination in fractured rock can travel great distances very quickly. So you have a really fast time of travel. Really, really important that you understand this and you look for this ahead of time. Because the last thing you want to do is to put a well in when you know there's contamination there, and the well, you put a well in and you've wasted a lot of money and a lot of time when you could have prevented it by understanding what's going on. PCS is a little cartoon here, all different contaminants, landfills, which we know are a major source, underground storage tank, gas stations, you know, septic systems, agricultural fields, all these things, hazardous waste dumps. You know, we see the smokestack up here, and you know, maybe we don't think much of it, but there's a lot of stuff that comes out of this. Locally around here, we're finding a lot of these PFAS contaminants are airborne contaminants as opposed to, you know, what's happening, what's being put in the subsurface, but they are blown distances away from the facility in which they're formed, and the PFAS is being airborne and actually hitting the ground and contaminating the subsurface. PFAS is a major contaminant that we're all looking at right now, and you just have to look for these everywhere you go. Anything that touches this ground surface on the surface that I circle around is eventually going to end up in the subsurface, whether it's in the sand and gravel aquifer or in the underlying bedrock system. So hence, really look at all of this to understand what's going on. Frank showed something similar to this. You know, why do I need to worry about this, you know, in terms of contamination? Well, here's our recharge up in this higher area in mountains, if you, in this particular case. It may only take years for some of this contamination to get to this location, maybe, you know, centuries to get way down here. You know, there's a scale over here. You know, it could take, you know, thousands of years to get certain places. So this contamination is there, and you may think it's gone, but it's still around there. And sometimes it doesn't biodegrade or break down, so you're left with this contamination that exists within the subsurface. It hits the bedrock system, and depending upon the number of fractures there, it can be there. It can get stuck in fractures and remain there as a point source of contamination for long, long periods of time. So best to do as much upfront work to develop your model, to develop an understanding, so that you don't get burned later on. Once you've done all that sort of upfront stuff, then it becomes the really cool stuff. Fracture trace analysis. Let's look at air photos. Let's see if we can identify photolinears on this air photo. You have detailed mapping. You can put some stuff on this. Geophysical surveys, very low frequency geophysics, resistivities, magnetics, or EMT, which is electromagnetotellurics, which is a really, really powerful tool that is not used very much, and we can talk about that later. And then once you do that, you have to get out in the field and field truth this to find out, boy, did that fractured lineament that we picked up, is that a stone wall? Is it some sort of road that's out there in the woods? What is it? So you have to get out there, back out in the field to look at these things. And then you have to refine that conceptual hydrogeological model based on all the information you've gathered. You know, do I need to enlarge it, make it smaller, modify the boundaries? What do I need to do? And then finally, sort of select your drilling targets, which is the fun part, but yet can be the most frustrating part as you start drilling. Now, for me, I prefer using black and white photos, aerial photographs at 1 to 500 scale for the sites I'm looking at. Color ones work just fine. I've used infrared ones in the past. I use sometimes different age ones. So I can use the most recent one, and I can use ones that are older than that, just to see culturally how things have changed over a period of time. Things that I can pick up and see. In this particular case, this sort of where I'm drawing the little pointer down here, this is actually the ocean coming through here. So I have to be mindful of this estuary, these tributaries going back up in here. In terms of siting a well over here, am I going to be picking up salt water as I do this? Or is there a sufficient groundwater, freshwater head that's pushing everything out in this direction so I don't have to worry about it? So this is just my preference in using it. I've used different scales, you know, 1 to 2,000, all different ones, but preference is this particular scale for myself. No, this is not little pickup sticks on top of your air photo, but rather this is actually fracture traces that I've picked up on this particular air photo. Some people use the look at air photos in stereo to pick these up. I don't do that. I've been doing this for a long time, and I tend not to use stereos. I can, but I prefer to use a single air photo to pick up the linears on there. In this particular one, there's a huge number of intersecting fractures out here. And remember, in fracture systems and bedrock systems, the more intersecting fractures that you have, the higher the probability that you're going to hit water and larger quantities of water. So this is a good particular area back here. This is the area of concern that we were looking at, that's sort of outlined here. This, and that's why there was nothing over here, because we didn't look over there, because there is actually a large Walmart right over here, so we didn't want to go near that. So this was the area we particularly looked at here. So fracture trace analysis, do fracture traces relate to local or regional structural trends? This is what you have to identify. The orientations that I'm looking at, are they related to a regional trend, like a northeast trend that we typically see around the northeast? And typically we see ones northwestward, which are orthogonal to that, which is just picking up the structural regional trends that we see. Are the lithologic contacts? This is really critical, at least around here, because we have dissimilar rock types and they have different competencies. And so I may have, a granite against a metavolcanic that has fractures differently. And along contacts, I may find a lot of different fractures and a high density of fractures along that contact. So look at that, be mindful of that. We'll look at that in a little while. And what about the PCSs? What do I see here? How do these fractures relate to potential contamination sources? And do any of fractures cross over into those boundaries? And if that's the case, do I want to keep moving forward with this project? This particular one is just showing fracture trace with the VLF, very low frequency geophysics. I like using very low frequency geophysics a lot. It's been a pretty powerful tool, at least up in the Northeast. And the possible fracture zones, are the ones in red, are the ones that are picked up from the VLF. The other ones in green are the ones that I picked up are the lineaments from the fracture trace. What shows up on this is that a lot of the linears that I picked up are parallel to, not necessarily the same coincident with each other, but parallel to what the VLF has picked up. Now this is good because the VLF sees below ground surface. I'm looking at surface features. It's looking at down to like 250 feet or so, plus or minus, in the subsurface. So if I look at the linear I pick up and I look at theirs, is this suggesting to me that the fracture is dipping off, in this case, to the north. So at depth, it's going to be down here, as opposed to if I drill here, I may not hit it. So maybe I need to go here or a little bit in this direction to go a little bit deeper. We see it in a number of different directions here. So you just have to say, you have to gauge with experience where you think the best place is to look at this. So if we focus in on one of these areas, because there's so much information here, if I focus in on an area and say, okay, well, let me look. So I've gone through here and I can pick out numerous different intersections where I would potentially like to drill. But then I focus even more in on that to figure out what are the higher probability ones that I want to look at. So this is compiling the information from BLF, from fracture traces. There are no rock exposed out here. This area is overlain by probably upwards to 30, 40, 50 feet of marine clays. So there's no bedrock exposed here at all. Now, compared to this last one, this is a site that has very few fracture traces, just not too many at all, and that I was able to pick up on the air photos. And then with the geophysics, we're finding, okay, well, some of them are kind of parallel to what I'm looking at. They're kind of in the same direction. What do I think? So in this particular case, I actually used the VLF. The VLF results to actually select the locations because they were kind of parallel to what I was picking up. So let me look at these locations. So that's what I did here, and I selected, in this case, half a dozen or so locations. Ultimately drilled the one where it says well 20 and well 21, and we picked up about 200 gallons a minute here at well 20, and over here at well 21 picked up about 250 gallons a minute. So fairly close to each other, probably 400 feet offset from each other. So here you have very few fracture traces to work with, and not so much VLF linears that you're dealing with as compared to the last one that we just saw. This is my favorite. It's called EMT, electromagnetotellurics. It uses telluric waves from the sun to look down into the subsurface. The telluric waves penetrate the surface. This is the only methodology I've been able to find where I can actually see where the fracture zones are at depth. I didn't believe this at first until we started working with this, and I didn't tell the drillers where I thought the fracture zones were and how much water they were going to hit, and I just let them drill it off, and this is what they found. They were essentially within plus or minus 2 feet of the fracture zone and fairly close to the yield at that particular fracture. So it was pretty nice to see this, but unfortunately the person who developed this would not share the technology and passed away not too long ago. So it's kind of, if anyone knows how to do EMT, this would be great. Please resurrect it. Thank you. Conceptual hydrogeologic model. This is for a 500 gallon per minute bedrock source. These wells are located right in this area here. And the conceptual model comes and shows an area about like this, where this blue line is. And this is based on information we have from drilling and based on topography too. And then if we come down here and we look at this brown line, well, this is a surface water drainage feature for this particular pond. It's very limited in size, but note that the hydrogeological model for the wells cuts across this boundary and essentially ends at a hydrologic boundary, which is the pond itself. So although during the pumping test, there was no drawdown associated with any of these wells or close to the pond, nevertheless, we just drew it to the edge of the pond to be conservative in this case. So this is what it looks like. This one is an unusual one in that it's fairly circular. Why is it circular? It's circular because the rocks that are here that have been intersected are close to a geological contact, but also are highly fractured and tend to behave more like a porous medium than they do a fractured crystalline bedrock system. So compiling all the data, property boundaries, in this case on white that we show on the diagram over here is a property boundary. It's about 200 acres in this case. The geology here, we see it's called the Roxbury conglomerate up here, and we have the Cambridge argillite. This is in Boston, and we have this major fracture fault zone, which is this black line, essentially trending north-south throughout this. We have the fracture trace lineaments in yellow that I've drawn here, and I've also shown the drilling targets, which I've labeled, A through F, and this thing at the end here called PCSs. Well, these PCSs are what shut down this project because the potential, this is in the Boston area, and the potential for drawing in contamination along these fractures into this area, which happens to be a major, it's called the Arboretum. So there are lots of trees, lots of vegetation in here, and it's been around for many, many, many years, owned by Harvard University, and they did not want to have the potential to bring water in for irrigation and spray it on all the trees, et cetera, that are in here and have the potential to contaminate them or to also draw contamination onto that property. So even though we went through all of this, ultimately it was the PCSs that stopped this project from going forward, even though we had great geological information, really good fracture traces, geological contacts, so a lot of positive things, but the thing that shut it down was the contamination. So let's drill now. This particular one that we see on the left here is not an artesian one. Why? Because the water level in this particular well does not go above the bedrock overburden interface, so we have to pump this water out. We notice we have sand and gravel. We have a till boundary below that, which is fairly common in glaciated terrains. And then we have a bedrock surface. We have our casing going down. You know, in this case, we like to go 15 to 20 feet into competent rock. You know, regardless of what the regulations say, we would rather be safe than sorry. So we'll go a little bit deeper than we have to into rock, just to be safe. We also see that the fractures that have been intersected in this particular one, there are major fractures in here, which intersected the water down here, more fractures down here. So we have major fracture zones in through here that are contributing virtually all of the water in this particular well that we see here. You know, can fractures, a question I get asked a lot, can fractures be traced for long distances? And really the simple answer is no. For example, we've drilled wells within literally 5 to 10 feet of an existing well and trying to intersect the same fracture system and have missed it. That's even after doing downhole geophysics and everything that we need to, we've missed that fracture zone. The other thing which is kind of scary in bedrock systems is that the hole is not always vertical, plumb to the ground, you know, vertical to the ground surface. In many cases, it tends to drift off to some direction below ground surface. We had one that was drilled by someone else, and it drifted 90 feet off vertical. So that's a lot. And so you think you're hitting the fracture zones you want to, but you may have totally missed them because the hole is not vertical. When you do hit water, though, and you put the pump down, sometimes the pump will not go down because there's so much curvature in the borehole that you cannot get the pump down into the well. That's the real problem. That's a real mistake that you don't want to make. One of the things to do to try to eliminate that is have the driller drill slowly and not try to put a lot of downhole pressure because that tends to deviate, and they don't know it's deviating very much because there's so much flex in the rods going down. So be careful when you do this, but the simple answer is, you know, cannot be traced for long distances. And final, I'll leave you with this, that there is no crystal ball here. You have to do a lot of work, upfront work, be patient, be pragmatic. Draw on as much knowledge as you can to people around you to try to understand this. I know a lot of this is not taught in schools. How do I know this? You know, I've got to a lot of GSA sessions where I have to, you know, evaluate poster sessions and stuff like that. And I'll ask the students, you know, well, they've tested these wells. I said, well, how did you know where to put the well? And the response is, well, the well was already there. And it's like, well, but how would you go about finding the well? And they just don't know. And so things like this should be taught. You know, I try to do this, you know, I'll teach a graduate course at University of New Hampshire once in a while, and I try to give sort of applied information as opposed to, you know, equations and stuff out of a textbook, because this is the real world that we deal with. But there is no crystal ball here, no matter how many years you've been doing this. You just have to keep trying, and hopefully you'll be successful in what you do. So I'll leave it there. Questions. I want to thank everyone for being here and being patient, listening to us. I apologize for my technical glitches before this. And hopefully you'll be able to join us next week when we'll go over a lot more stuff. Frank will be here. Ted Marine will be here to talk about stuff. I'll be here to talk about the case study. So I'll leave with that and turn it back over to Leela.
Great. Thanks, Ray. I'll go ahead and share my slides here so we can move into our final question and answer session. So if you have any questions, please go ahead and unmute yourself and ask away. Or you can also type your questions into the chat box too, and I'll field them there. Ray, going back to your last slide there, talking about experience that university students, you know, what suggestions do you have for how they can gain experience doing phased approach projects? You know, is it something they can learn during internships? Are there any online resources or suggestions that you might have?
Well, I think online courses are good. I mean, something like we were just presenting today is a good introduction to this. I think if they take courses away from the university, that would be great too. If there's a faculty member in the department that has experience doing this, it would be great to have some sort of internship or special project that they can work on to learn some of this stuff. Or the faculty members can reach out to the various companies within their essentially striking distance, so to speak, to get them to come in and to talk about these things. We typically, when we have interns come in, we'll go to the universities, have them come in, and then we will take them out on sites. We will have them help run pumping tests to show them how to do a lot of this work. So that's how we tend to do it, and we try to reach out to the schools to do this. And some of the schools are very receptive. Others, man, they don't have an interest in this.
Great, thanks for that. Here's a question for both you and Frank. Looking at state and local agencies, are there specific agencies that you'd recommend people reference when they need to pull some of the data for their phased approach investigations, as state geologic surveys, water resource agencies, Department of Natural Resources? Are there kind of common elements, at least where you guys are, in terms of the agencies that should be contacted to get this information?
Yeah.
Go ahead, Frank.
Right. Yeah, I was just going to say, I mean, Ray's kind of mentioned already, the USGS obviously is a good play. Everything's online now, which makes it phenomenally easy to do. And I think USGS, the state survey, and then you get down to either the Department of Health or, depending on what the acronym is they want to use, the environmental permitting groups will have a lot of that stuff available too. And I've noticed just, it's just amazing the stuff that's currently available on GIS and links to all of these different databases, at least in the Northeast. I mean, every state has just like more information that you know what to do with sometimes. The thing that is missing, and Ray, you obviously, I'll hand it over to you in a second, but that I've noticed is if you're looking for information like the actual data, sometimes logs are kind of skimpy. You'll have completion information, but not the logs. The other thing might be pumping test data. You don't see a lot of that. You may get the interpretation results in terms of the aquifer characteristics and so forth, but it would be nice to be able to get the data, because sometimes there's something that you want to do with that that's a little different than just taking an aquifer characteristic verbatim. But that's in terms of what I do, in terms of those are the particular groups that I rely on heavily.
Yeah, I'll just echo what Frank said and what I said earlier. Like the USGS stuff is probably the most critical to use. The other thing too is if some exploration has been done for a particular client, but they haven't submitted anything to a regulatory agency, they may have a lot of this information in reports that they have. Sometimes reports are just stacked up, put somewhere, and no one even knows, because they get changes of personnel, so they don't even know it's there. But it's always good to ask, what have you done in the past? One good thing to do is to say, can we compile all your previous exploration work that you've done, and so that you can get an understanding for where they've worked, what they've done, and then have a look at some of the data Frank was talking about, the drilling logs, the pumping test reports, what they've looked at. For example, one site that I just showed you, a little bit on with it, we didn't have many fracture traces or a lot of VLF results. Bedrock wells had been drilled there in the past, but had not been successful. And we decided to say, I think we need to take another look at this. Why did we take a look at it? We looked at it because, one, the client owned all this land, and two, we could see that the water quality in the overburden wells, which are close by, was not too different from the bedrock system. So we thought, well, we know bedrock water is discharging to this area. We just have to find a spot where we can intersect fractures where we'll have this water. And we were able to do that, even though prior to that time, it was probably 3, 4, 5 different bedrock wells were put in, and none of them intersected any water. So it's good to check everything that you can.
Great, thanks for that. Do we have any questions from the audience? Just Going to throw that out there, and you guys want to unmute yourself and ask a question. Okay, I've got one here about fracture trace analysis. Is there a benefit to using black and white photos over color photos? Do you have a preference, and if so, why?
Well, as I mentioned in the presentation, I prefer black and white, although I've used virtually everything in the past. Black and white, one, they're easier, mostly easier to get, and I can get more generations of them because there's so many, they're being flown so often, every several years. So I can get a lot of them, and they're not always directly over the area you want to look at. So they're, they can be off different sides and locations. So I can get different look at fractures from different locations, different shadows as the sun's hitting it, different times of the year, hopefully when the leaves are off, because then you can see more. I'm able to pick up, as I'm sure a lot of people are, fracture linears, even if the ground has been tilled and farmed for 200 years, you can still see the features in the subsurface. But that's just me. But I prefer black and white. Color, infrared, doesn't matter to me though.
Great.
Yeah, I would echo that. The only thing I find the false color infrared kind of handy for is sometimes if I'm looking at spots that have a particular dark tone to them, and the false color infrared kind of highlights whether or not it's a high moisture area. And just to kind of, just tag off of what Ray just said there, sometimes they can correspond to like seeps, areas where there may be groundwater discharge. And, they may help you with respect to looking at your, prioritizing your well sites based on the types of fracture traces you're finding.
Great, thanks for that. Well, we're coming up on the hour, so that's about all we have time for today. Thanks everyone for the great questions, and thanks Ray and Frank for the good discussion there. Just as a reminder for everyone, you'll be notified when the CEUs will be issued, so stay tuned for that. And just be aware that you need to have watched at least 70% of today's webinar for those CEUs to be awarded, but I think everyone's been here since the beginning, so we're good there. And if you have any questions that were not addressed today, you can go ahead and email them to us at webinars@americangeosciences.org, and we'll forward your questions along to Ray and Frank. And our next webinar in this series is next Thursday, October 31st. So please stay tuned for that. In the next webinar, we're going to have Ray and Frank and Ted Marine covering bedrock well drilling and well construction, talking about pumping tests and safe yield estimates, and also going over a bedrock well development case study. So that's going to be really interesting, and you can go ahead and register for it there at www.americangeosciences.org/webinars. And if you have a few minutes today, we would love to hear your feedback about what you thought of this webinar, and you can share your thoughts with us there at the bit.ly link, bit.ly/evaluation-bedrockwells1. So thank you everyone for joining us today. This concludes our webinar, and hopefully we will see you next week at the next installment of this series. So thanks again, Frank and Ray.
Thank you.
Thank you.